So we're looking at pressure sensors. Of course, we know that by now, hopefully, we know the definition of a sensor. This is one of the models that we use. And so these are the things that we came up with, what we need to sense. And this does by no means that there's not sensors out there that don't sense other things. And of course, we've come down through and the ones that we've gone over. So, but we're not going to do viscosity or moisture or thickness. Count, you can count as an electronic circuit anyway. Orientation, we might have time to get into these. And of course, how to sense the level of gases. We're not talking about height, we're talking about the amount. So pressure, a difference of potential applied perpendicular to a surface of an object per unit area over which the force per unit area that one material exerts on another. So we use the term force as pressure. They're not the same, right? Don't understand that. But they basically have to go together, right? Understand that. It would be like your heart and your lungs. They're not the same, but you wouldn't be without, you wouldn't have a heart, you wouldn't be here, and if you didn't have lungs, you wouldn't be here, right? So basically, we don't really have a force without a pressure, and we don't have pressure, normally we don't have pressure that don't exert a force. That makes sense? First of all, we need to learn about the different types of pressure. 1 atmosphere pressure, some people call this atmospheric pressure. This is the average pressure at sea level, assumed to be 14.7 psi, or 101.3 kilopascal, or 1.1 bar. And that's up for discussion too. What I found is a place here, and we'll go up to this guy, and this discuss pressure in different things that what they think 1 atmosphere pressure would be. And what I'm trying to do is get down to this chart right here. So we got all these standardization of organizations that standardize this thing. But what we look at, and we look at pressure at sea level, and this organization, IUPAC, it says that it's what? 5038. They say that's sea level pressure. This organization says it's what? 6959. This organization uses that. This organization uses that. Where am I at? This organization uses that. This organization gets this type of what? 14.5, 14.5, 14.5, 14.69. This guy right here is rounded a little bit. 14.69, 14.69. This guy says it's 14.73. This says it's 14.7. So what we're saying is it depends on where you are, who you use. So basically, 1 atmosphere pressure can be between what they say 14.5 and 14.7. Now, what we use, and you can see there's very, very little. We're in the fractions right here. But we're talking about, 200 milli between the minimum and the maximum. So what we use normally over here in the USA is we use one of these guys right here. And notice another thing that they give you is people don't understand is pressure is also determined by temperature. So if we got the same volume of air, And pressure varies with temperature. If temperature goes up, pressure goes up. If temperature goes down, pressure. And we understand that even in our atmosphere. So we have what we call low pressure and high pressure. Well, what's high pressure? What determines low pressure and high pressure? It's a difference in temperature, right? You understand? So the hotter the temperature is, the air has a tendency to rise and creates low pressure. The cooler the temperature is, that does what? The air gets heavier and it falls, and that's what low pressure and high pressure. We get into trouble when they come together, right? So that's where we get bad weather. Especially when the pressure differential is a lot. The different pressure is a lot, and you get a lot of downflow, and as soon as it hits the ground, it does what? Shoots back up, and you create this circulation, of course, which causes rain. So notice just about every one of these is at a given temperature. Some of them say the temperature is freezing. The weight of air is freezing, so that would be 0 degrees centigrade or 32 degrees Fahrenheit. Some of them say that. Some of them say 59, some of them say 68, some of them say 72, 77, 68. So you can see the range of temperatures where they set these standards are a lot too. Are they saying it? So if we was to look at our average temperature over a year, then that's what we use. But what you got to understand is that atmospheric pressure is constantly varying. So we got to come up and we got to use a standard that's good, right? But it's not perfectly accurate. So when we start doing so what we do is we use 14.7 psi, which this would be rounded to anyway, right? So we use 14.7 psi for what we call 1 atmosphere. That makes sense? Everybody okay? Let's see, it's all over the place, right? You understand that? So we're going to use 14.7 psi, which is 1.4. Now, 14.7 psi is U.S. customary. So we'll look at that later on. So basically, guys, we're about the only people in the world. There's only 3 countries that use psi as their standard. Anybody know what they are? It's called U.S. customary, so you're pretty sure which one of them is. And this, Myanmar and Liberia, those are the only 3 countries that use U.S. customary as their standard. Pressure sensors. So pressure sensors usually consist of 2 parts. We have a sensing element, and this is pretty true about a lot of our sensors. We have a sensing element, right? You understand? That senses, and then we have the element that takes that sensing element and converts it over to electrical signals that we actually process. Are we okay? So we gotta have something that has the ability to sense pressure. So these are the type of pressures we have. We have what we call absolute pressure, which is PSI, lowercase letters. This is relative to 0, which would be a perfect vacuum. So right now, if I had a gauge in here that measured PSIA, it would be showing 14. Right now, it would be showing 14 point something pounds. Right? You understand? Then we have gauge pressure. This is probably 99% of the gauges out there. This is relative to the atmospheric pressure, and we're going to use 14.7 psi, even though we know it can vary a little bit. Normally, these things are set up. So here, if it shows 0, it means the gauge is actually seeing around 14.7 psi. That's gauge. So at 14.7 psi, that guy shows pressure, shows 0.
One of the classes I had was
probably fluid power. You have fluid power? Hydraulics, pneumatics? Yeah.
I'm sitting there thinking, we had to calculate it.
Yeah. Fluid power, we deal with this a lot too. People don't understand what's going on with the pressure. Then we have vacuum. Anything below atmospheric pressure would be considered a vacuum. A differential pressure, this is the pressure between two differences. Then you have seal pressure, this is relative to fixed pressure. Y'all understand that? Is everybody okay? Yes, no? Any questions? So, so if I had an absolute pressure gauge in here and I was holding it in my hand right here, it would be showing 14.7 psi. Because when we say 14.7 psi, where does that react on? That reacts on all surfaces, on all different angles. So right now, where do I have 14.7 psi of? I have it on the bottom of this chair. I have it on the side of this chair. I have it on me. I have it on my head. And of course, as soon as I pick my foot up off that floor, I have 14.7 psi. So pressure is at right angles on anything that's going, right? So I mean, if I had an absolute pressure gauge in here and I had the bottom opened up so pressure could come into it, it would be showing about 14.7 psi right. If I had a gauge pressure gauge, then I would be putting on here, I'd open it up, it would show me 0. So on gauge pressure, the atmospheric pressure is subtracted out, right? So your pressure is relative to, it's relative to 14.7 psi. Right, you understand? So if I measure the pressure on a liquid and it's showing 1,000, I'm looking at a gauge pressure gauge, it's measuring 1,000 psi. There is actually 1,014.7 psi. Y'all understand? So gauge pressure is always off by atmospheric pressure. Now we're using 14.7 psi. But if I was up in Boulder City, I need to get that. I've got it from Birmingham. But like Boulder City, if I looked at the atmospheric pressure there, it's going to be probably around 14.5, right? Down here, we're pretty close to the what? To the 14.7 right here. So what we're saying is that gauge pressure is relative to 0 is relative to that the pressure that you're at. That's what it says 0 is. Right? Understand? Absolute pressure is relative to 0. That means a perfect vacuum. Everybody understand that? And then of course differential pressure should make sense. So I'm trying to see a difference between the pressure on this pipe and the pressure on that pipe. So if you're ever into air conditioning, you know, and you ever feel, you ever go out and work on a true air conditioning system, you hook your gauges up to the high pressure side and the low pressure side. And so what your gauge is measuring is the differential pressure between the high pressure and the low pressure, and that shows you how much Freon you're supposed to put into your system at a certain temperature, by the way, guys, because gases, pressure varies with what? Temperature. So if you ever worked at an HVAC system and you did it right, and you look at those gauges, and then you do a formula that compensates for the temperature that you're at, and then that's how much Freon you put into your system. And of course, seal pressure, you decide on seal pressure what it's relative to. So in one side of the chill chamber, it might have 15 psi, and then you come in and you put a differential pressure, and it would be relative to 15 psi, right? You understand what we mean there? Everybody okay? These are the different units we have. Of course, most of us are familiar with PSI. You go out there and you put air in your tires, you can play with what? PSI. The other method that we have is called inches of mercury. Also, it could be called a torr. So 1 torr is equal to 1 millimeter of mercury. Right? So if I had 2 torrs, it would be 2 millimeters. We have inches of water. And then, of course, we get into the SI units, which would be what? Pascals, bars, and then kilograms per centimeter squared. Which is basically way of representing. Are we okay? Right, okay. Yes, no. A U.S. customary, this formula, by the way, applies. We have a law out there called Pascal law that basically says that the force applied to a liquid, or the force applied by a fluid is equal to the force times the area. That way, you'll run into that a lot, especially with power. Well, we can rearrange that and come up and say, okay, pressure would be equal to force divided by area. So if I can measure a force mechanically, and then I can divide that by an area, and this is the way we have to measure pressure, right? So we're not measuring pressure directly, we're measuring pressure indirectly. By doing what? Measuring the force, and then we have to know the area that force is being. U.S. customary, the pressure resulting from the force of 1 foot-pound force applied to an area of 1 square inch. So that's the way we figure area, right? Force, something that tends to cause a change in motion or shape of an object. Everybody okay on those definitions? Pretty straightforward. Hopefully I've heard them before. So this is inches of mercury. So it says the pressure exerted by, now normally this is done electronically now, but the pressure exerted by a cylindrical column of mercury of 1 inch in height at 32 degrees Fahrenheit, or water at 39 degrees Fahrenheit. Now how they come up with that, I don't know. Like a standard acceleration of gravity. So this is relative to gravity. So gravity is trying to make it move, right? You understand? And then so it's the difference between the acceleration of gravity and how much mercury does. And we run into this all. Where do we run into inches of mercury? Where did y'all see that at? Nobody knows? So Pascal, we'll look at this in Pascal. This is the international standard. The pressure exerted by a force of magnitude of 1 Newton perpendicular upon an area of 1 square meter. And this is the international standard. This is the international standard. Now the problem we have is that newtons are really, really small. So 1 psi equals to 6,895 pascals. Normally when we get into pascals, they're not going to be pascals, they're going to be what we call kilopascals. They would be what? Yeah, they would move this over 3 places, right? And say 6 point, or they'd say 7 kilopascals. Right, you understand? The problem we have is that this guy right here varies, because one of them says PSI is 4.7. One of them says atmospheric pressure is 14.7, and then we go all the way down to 14.5. So this is only true if you're using these guys right here for your standard. If you're not using that as your standard, which we don't use, then we're going to use, where am I at? Right here. So if you use 14.7, then it's 101.3 kilopascals per, right? Yeah, you understand that? If we use 14.7. If we use 14.5, then what that thing says is true. That makes sense? You understand? So what has happened is this guy right here has changed things. So before 1982, this standard organization right here, I'll put this link up there. This is actually this guy right here. It's the International Union of Pure Applied Chemistry. Before 1982, they used the 14.7. But the problem with the 14.7 is the bar kilopascals is right here. Understand? If they say it's 14.5038, then 1 kilopascal would be equal to 100. then of course that means a bar would be equal to 100,000 pascals would be equal to 1 bar. Does that make sense? So where are you going to run into this? Well, here odds are we're going to use this guy, we're going to use this right here. Right? Or probably we'll use this guy down here, American Association, because this gives us a reliable temperature. So the American Association of Physics says that instead of about what temperature, but still the numbers still line up, which is very, very great. So we're going to use 14.7 psi, and whether you use 100 or it's not going to make that much difference, especially when you start looking at our indicators, because you're not going to have enough resolution on our indicators to make a difference between 100 and 100 and 101, right? Does that make sense? Oh, what am I doing? It's not tabbing. There we go. So here it's saying 1 bar is equal to 1,000 pascals, but it depends. It could be 1,100, right? I'm sorry, 101,000 if you use 47.5, right? I'm sorry, 14.7. If you use 14.5, then this right here is different. So I put that out here. These standardization organizations use 14.5 for sea level. And you notice everybody else uses basically 14.7. So we're using 14. So 1 kilopascal would be, we're familiar with this, right? So we just take the number of pascals and divide it by 1,000, which means you just move the decimal point over to the left 3 times, right? So you're not going to see any pressure gauges in pascals. That's going to be kilopascal. So 1 kilopascal equals approximately 1.45 psi. That means, or it could be 14.7 psi, whichever way you look, right? You understand that? Okay, there. So I don't know where this came from. And of course, 1 psi equals 6,895 pascals. Newton, the force needed to accelerate 1 kilogram of mass around a rate of 1 meter per second squared. So we're going to see this used to kilograms of meter squared. We'll see this. We'll see different types of measurements. Luckily over here, and this is a chart by the way, I forgot where I got this thing. I needed to go back and find it so I could give the people credit for it. I need to come up with it. But these are our methods of measuring pressure. So we have the millibar, we have the bar, we have the atmosphere, which could be 14.7 or 14.5. We have the pascal, we have the kilopascal, we have the megapascal. We have the millimeter of H2O, the millimeters of water. We have inches per water. We have millimeters of mercury, inches of mercury, and then it's kilogram per centimeter squared, which is newtons, right? Everybody okay? Huh? Could be used for torque, right? But that's Newton is actually a force, right? You understand that? But we can't have pressure without what? We can't have force without pressure. So kilograms, weight times centimeter squared, this would be basically taking Newton and converting it into a pressure. Does that make sense? So we can look up this. So from 2, so 1 psi would be equal to 1 psi. So I could go to millibars by multiplying psi times 68.95 bars, but for the same thing. Atmosphere by 0.0681. And notice they've rounded that number. Pascals, we know kilopascal, megapascal, milligrams of H2O. I'm sorry, millimeters of H2O. This is H2O, and this would be, so we can go, we can look at this line, and we can go, and I've got a calculator, that I downloaded, a free application that I've got on my cell phone that converts units for me. And I use it every once in a while because these charts are nice, but you still gotta have these charts. So if you work in this field and you get out there and you see a pressure gauge that's in nothing but bars, you don't understand bars, then you're going until you learn it. Now, odds are if you're around it a lot, then over time you'll be able to picture that in your head, right, and understand. It's just like if you learn a foreign language, you know your language, and what you do is you relate it into a word, and then after a while you see both words in your head. So these is what we're up against. So normally over here, we have our gauges, especially in these companies where we have multiple crafts or multiple nationalities working in there. Most of our meters, what you're going to see is a lot of them you're going to see that's got multiple scales on it. So the one on the top left, by the way, did y'all see the wood in there? Yeah. When I first got involved with this, I saw that and I called up the company and said, there's fluid in my meter. He says, guys, he says, that's a gel. He says, it's in there to dampen the meter, so the meter doesn't vary, especially on compressors and pumps. A lot of times they do what? They generate a jerky movement and your meter will be jerking back and forth, wear and tear. So that's just a dampening gel that they put inside the meter. So that was funny. So most of the time you see this meter, they're going to have that gel in there, right? So notice the one on the top left is in PSI. Can y'all see this one? It's got two scales on it. It's got bars. A bars is a representation of a 100 kilopascals. So one bar is 100,000 pascals. So you're not going to see pascals a lot. You might see this 1,000 times. You might see kilopascals, but a lot of times you're going to see bars. BAR, right? You'll see that. So 50 bars would actually be what? About 5. We take this and multiply by that, right? It'll be 500,000 kilopascals. So that's going to be about 5 million pascals, right? So pascals is a really, really small unit. And you see why we don't use very many pascals. We use bars a lot because one bar equals to 100,000 pascals. But if we come over here, this is PSI. If we come over here and look at this, and we do our conversion factor, see here they almost line up, right? But this would be bars or pascals. Bar is just the way we represent pascals, right? You understand? It'd be like I say meg on resistors. So instead of saying 1 million, we say 1 meg.
So PSI is the black on the top.
Yeah,
PSI.
so you can see the scale. So this is blue. It's hard to see on my PowerPoint. But normally what they do is they put the scales in 2 different colors. Normally they put the bars on the inside, or the kilopascals on the inside, and the PSI on the outside.
50 bars, that's equivalent.
Well, we got, so this is 500. We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 between there, right? So each one of these would be worth 500, right? So it'd be 510, 520, 530. One of these would be 10. So each one of them would be worth 530. So what would that do? If it measured 500, how many bars would that be? Oh, you said 50.
50 bars, yeah, I'm looking at
50. Then of course over here, this is then PSI. So each one of these would be worth 50, right? Because we got to go to each one of those would be worth 50. Is that right? There's 10 between 500 and 1,000, that'd be 550, that would be 600, 650, that would be 700, so about 750 PSI would be equal to 50 bars. It would be a little off. If you could look, you could see that the picture is
On the two lines down there, I don't remember seeing a gauge anywhere other than maybe if there's an air pressure. Is there a gauge or something?
that is the pressure gauge. I don't know what your,
There is a gauge, and it's a pressure gauge, that's all we have out
yeah, every service unit that has a pressure regulator on it has a pressure gauge.
there.
They have pressure sensors, but they don't have gauges. So sometimes we have pressure sensors that don't have a gauge on them.
But what I was thinking is, some of these robots or whatever are made in foreign countries, and if they have gauges on them, we need to know how to convert ours to something that we can.
Right, or replace the
Yeah,
gauge.
whatever it is, we need.
Most of these threads down here are pretty standard size. So if you got a gauge out there that's in bars, then you could very easily go out and get the same gauge that's in PSI and just replace it. I've never seen a robot that has a pressure gauge on it. Normally our pressure gauges are on the source. So if you looked at the robot, but if you looked at the source, that's what we call the service unit. The service unit usually contains a regulator, because normally, especially on compressors, most compressors, not all compressors, we do have some continuous flow compressors, but just about all our compressors work in a span. So what do? So yeah, but they charge a storage unit up to a maximum pressure, and then they turn the prime mover off until it drops down to below a minimum pressure. So if we're going to operate anything that we're going to operate it below the minimum pressure, right, on the thing. So it means if my compressor cut off at 70 PSI, I'm going to buy air tools that are designed to run at 60 PSI. Because that way 60 PSI is guaranteed. But if I run it at 70 PSI, then what I've done is I'm decreasing the mean time between failure. I'm decreasing the amount of time because I'm running it above what the seals and everything. So what we do is we have pressure regulators. And what the pressure regulators do is I would set it at 6. I would set my pressure regulator at 60. And so your pressure regulator has a gauge on it that shows you the pressure of where you regulate at. And then your compressor might have a gauge on it that shows you the pressure the span of the pressure that it's operating at, right? Does that make sense?
Exactly like air compressor.
Yeah, most air compressors are like that. Now we do have some continuous flow compressors, but they're pretty expensive. And they give us a constant flow at a pressure. But most of our compressors operate on a storage tank. And what we do is we compress air and store it in a tank. And then we use it out of the tank. Well, good questions, okay? Yeah, I mean, I've had to replace the pressure gauge on my compressor. When somebody dropped something on it, broke it off. I got one at Harbor Freight. This is in PSI, and this is in kilograms per centimeter squared, right? And then this right here is in inches of water. And how many of y'all have one of these? I've got a big one. But nobody really looks right here and sees what this is. MMAQ. So your blood pressure is measured in what? Millimeters of mercury. Most people don't understand it. So if I was to convert that to PSI, if I've got 128 or 51.7, then my actual pressure would be 2.4 PSI. If I've got 70 over 51, which means you got problems, right? My blood pressure is 1.36, so it varies. People don't understand that. They just know my blood pressure should be, bottom number should be lower than this and the top number should be lower than that. They don't understand that it's actually the mercury. And what do we get this all the time. So here's Birmingham weather right there. And they give me what they call the barometric pressure. What is barometric pressure? So our barometric pressure right now, we're at 75 degrees, and our barometric pressure is 30.09 inches of mercury. So barometric pressure is given. So what would be the atmospheric pressure in Birmingham? So 30.09. So I'm gonna come back here, and I don't know. I'll look at my chart. I just know it's somewhere close to what? We're pretty close. We're not too high where we're at. It's pretty close. Should be pretty close to sea level. So let's go back to our PowerPoints, and then we'll look at our conversion factor. 30.09. So 30.09, I'm going to go from inches of mercury over to PSI. So I take the 30.09 and I multiply by 0.0193.
And it's 0.49, yeah.
What's that?
2 inches of mercury. And it's 1 line below it.
Oh, I'm sorry. Thank you. 0.4912.
Oh, 0.49.
Yeah, I was on the wrong one. The one talking. 42, yeah. We're right at sea level pressure here, pretty close to it, right? Is that okay? So y'all use inches of mercury all the time. You know, every time you go to the doctor, one of the first things they do is check your blood pressure. And then, of course, you listen to the weather all the time, and they talk about, 30, 39, 30. They talk about the barometric pressure, right? So we already know, and this is pretty close to just about every sensor we have. We have some type of watt sensing element. Then we have a transducer. A transducer is a device that converts it from one form into another form. And then we have some type of signaling conditioning. Take output of the transistor and then gives us a V out. Signal conditioning could be taking the analog output of a sensor and converting it over to digital, or it could be giving us a true analog output, right? Everybody okay? Yay, no? Yay, nay? So these are our main sensing elements for pressure. We have something called a Bourdon tube. Then we have a diaphragm. We have a capillary. So this is a diaphragm. This right here, I think, is solid state. So Bourdon tube is a helical Bourdon tube. Helical means it's in a coil, right? Isn't it? Then we have a flat diaphragm, which is what we got. Then we have a convoluted diaphragm, capsule enveloped. We don't have this one, that's the thing. We do have the bellows and the diaphragm, and we do have Bourdon tube. We don't have a helical Bourdon tube. So we know that, so what we're going to do is we're going to take these devices, we're going to apply a pressure. The pressure is going to cause something to move, right, on this and that, against an area. And we know the mass, and we can calculate that. Right? The pressure is equal to what? Force divided by area. Transducers can be potentiometers. They can be piezo. Piezo means pressure. Piezoelectric or force. We can use inductive, we can use an LVDT, we can use passive, we can use piezoelectric. I got that in my class. So these are board-on tubes. So we have a thing that's shaped in the C where we have something twisted or we have something healed. We come in, we put pressure into the tube, right? You understand? And then it's gonna go around the C. And once this pressure is gonna cause it to do, it's gonna generate force. What that force is gonna try to do is gonna try to create a motion. The motion here is it's gonna try to make the tube straight. Come out of the C. Pressure would cause it to straighten up. The vacuum would cause it to come this way, right? Understand that? So this is a fairly old pressure gauge. And what we've done is we've taken off the cover, the actual indicator. So the pressure comes in through a tube here. Here's a board-on tube right here. Goes around the outside. You'll see that? And of course, this is where we can set our span. This guy used to run a mercury switch right here. And so we can actually come up here and set our span. So I have to set this up a little bit, guys, because it works off gravity. So I get up here, and when I get up to a certain pressure, it tilts it one way. And then I start dropping it down and dropping it down. And when I get below a certain pressure, it tilts the other way. So this is a board-on tube. Now, of course, here we have this would be digital, right? You understand? But we could come up here and replace this wiper down here. This actually moves proportional. Y'all can see it's moving proportional to the temperature. We could hook this up to an LVDT. We could hook it up to a potentiometer. We could hook it up to a lot of different things. So we can use this board-on tube as a sensing element. And then our transducer is either going to convert that over to electrical, and then we have our signal that's going to turn it into either digital or what. Hello. And we don't have any of the helical, but it works the same way. So the helical, what it would do, the helical would cause the thing to come out of the twist, right? You understand that? What's nice about this, guy, is we can connect this directly to a potentiometer. Here we would have to convert it over. Here they're using an LVDT. I could use a linear pot, or I could use a rack and pinion type of gear assembly. I know what a rack and pinion is. So we could use a rack and pinion type thing. We could have a pod. So a rack and pinion takes a linear mechanical motion and converts it into rotary or vice versa, right? So these are some board-on tubes. This is almost exactly like the one I got there, where we have the ability to set the span. This is a diaphragm type. So here they're using a calibrated spring. And when the diaphragm inside here moves, it just causes it to compress, and we can put that over there. Also, we can so this is a diaphragm type. So what we do is this would couple into our pressure, and it's got a calibrated spring behind it. So when the pressure comes in, what it does is causes this arm right here to move, and this would be proportional to the force, which is proportional to the pressure, right? You understand that? And then, of course, we could attach whatever we want to actually convert it over to a signal would be out here. Are you okay? Pretty simple. It did. They had a diaphragm on there. But notice if the diaphragm's in the center, then it can not only sense pressure, it could also sense a vacuum. And that was what was on your carburetor, was it was sensing the vacuum. I forgot about that. People,
That's automatic, of the 50s. Before that, you had a rod. Full with
yeah, what would happen is once your car cranked and it created a vacuum, it would open up. This is a bellows. So a bellows is just a metal. Usually it's metal, and this one's got a hole in it. But basically, we could use this to measure a differential pressure by putting the bellows inside a box, putting pressure on one side, which would cause it to contract, right? Put another pressure, which would try to cause it to expand. And where the bellows would end up with, it would end up with the differential, whichever one, right?
And on that is that pressure from incorporated versus the difference between.
Yeah, I mean, we could seal this off and put 15 psi inside this chamber, and then your pressure would be relative to 15 psi. And we could use this guy here both ways, right? You understand that? And I need to be over here on my PowerPoint because this is not being recorded. What I'm doing up here is not being recorded. So for differential, what we would do is we'd put one pressure in here and another pressure there. This pressure would try to cause the bellows to collapse. This pressure would try to cause the bellows to expand. And then what we would end up with is the position of the bellows would be equal to the differential pressure. And if we can measure that physical position, then we could do what? Then we can translate that into pressure. We could also seal this off and then put a pressure, go ahead and seal a pressure in here, like 20 psi. Or we could come up here and we could put 14.7 psi in there. And now my diaphragm would be absolute, right? You understand? Okay. So we could run it as seal, we could run it as differential. The one we got is just like this. So it's got a solid mount. This is differential. No, this is relative to atmospheric pressure. So atmospheric pressure would be coming up here and putting 14.7, which would be trying to do what? Push it in. And then what we come in here, this would actually start expanding it when it got above 14.7. So this right here would be, if I set 0 right here, then this would be gauge pressure, right? Okay. So here's a bellows and an application. This is a bellows that I have right here. I'm not going to expand this out, guys, because you can see it pretty well. So this is the bellows. This is the end that mounts, and you can see it's threaded. We bring our pressure in right here, and what's nice, it can measure a vacuum. So if I put a vacuum over here, it would try to cause it to expand, right? You understand? If I put a pressure in here, it's going to cause it. I'm sorry. If I put a vacuum in here, it's going to cause it to what? Collapse. If I put a pressure in here, it's going to cause it to expand above 14.7 psi. It's big gauge. So right now there's 14.7 psi pushing on this thing, try to make it do what? Collapse, right? So this is a bellows. This is a capsulated. Basically, it's just a thin metal like copper or brass. They got two plates. And what happens is when you put a pressure on it, it's going to try to do what? Collapse or expand, right? So it works kind of like a bellows. Now these are the sensing elements. These guys here, but a sensor, what does a sensor do? Takes a physical quantity and converts it over to electrical. So some of our sensors, we have to combine it with other sensing elements, right? You understand to get that conversion. Everybody okay? We do have some solid state sensors, piezoelectric sensors that produces a voltage when compressed or expanded. Piezoelectric sensors sense a change in pressure. The problem with piezoelectric devices, we have crystals that's out there, and we use these several times. is they generate an EMF when they are compressed or expanded. So if you've got a little cigarette lighter, if you do a clicker on there, so used to cigarette lighters, we had a flint and a wheel on there, and you'd spin it and generate a spark. We don't do that anymore. We use piezoelectric crystals. And when you strike that sucker, it creates a difference in potential that's pretty good, right? And it arcs across an arc, and that's what lights your fluid off. The problem is piezoelectric only generates it. If it was truly a pressure sensor, it would generate that voltage all the time. But it only generates that voltage when you strike it with a force, right? You understand that? So piezoelectric pressure sensors only look at what? When the pressure does what? Changes. So the pressure changes. So it's real good to look for pressure changes. We don't use piezoelectric to measure pressure. We use it to measure pressure changes. And that's what they're showing us here. So anytime you take this piezoelectric crystal and you expand it or retract it, it generates a voltage. But if we were to leave this stationary, then the output would be zero. That makes sense? Quartz crystals produce a difference of potential when compressed or expanded. It requires motion, not using static pressure systems. Used to measure turbulence, used to measure blast, used to measure ballistic, and used to measure engine combustion. But we don't use these guys to measure pressure, we use them to measure change in pressure, right? You don't understand that? How many of y'all ever used a lighter, even if you light your grill with it? Most of your gas grills now have a piezoelectric device on there. You press a button on the outside of your gas grill. You hit pop, right? And when it pops, it strikes that crystal. And when it strikes that crystal generates an EMF, a few thousand volts, and arcs across the gap, and that's what lights your gas off. But it don't do it when you hold it down, and it don't do it when you let it go up. It only does it when it sees that change in pressure, right? Real fast change in pressure. A piezoelectric, now this is, guys, a little different. No, this is not that. So this is a typical piezoelectric sensor. So we have a mounting nut, we have a connection, we have a 40 integrated amplifier circuit, mounting clips, and so I don't know where it is. But look what it's actually using to sense the pressure. It's using a what? This is a piezo-resistive. This is not piezoelectric. So piezoelectric creates a voltage. Piezo-resistive changes its resistance to pressure. So these guys right here are very popular because they're solid state. What does the term solid state mean? Usually we use, for years and years and years, all the logic that we did was done with electromechanical devices called relays. You're all familiar with relays. The problem with these devices is that they have moved, they're electromechanical, which means what? Now they have two ways they can fail, right? We're combining, and of course they're going to be slower because of the mechanics. So they started and came up with methods they could do this with electronically, with solid state or semiconductor devices. And these guys, well, originally solid state started off with vacuum tubes. I don't know if y'all ever seen vacuum tubes. They're still pretty popular in the extreme high power applications. And also a lot of your stereo enthusiasts don't believe in solid state. They like this vacuum, the mellow sound of vacuum.
You still buy those back?
Yeah, you can.
Like free of most anything?
Just about every vacuum tube is still available out there. Now they're really dang expensive because they're made on a very limited scale.
Well, I got two RCA radios, one that's this tall. And I could turn it on and I could see the light.
Well, the problem with it's not really a light, it's a heating element. The problem with vacuum tubes work off of a thermal emission. So what we do is there's a lot of materials that when you heat them up, they'll emit electrons. And we call it an electron cloud. So that little glow you see in a vacuum tube is the heater. And it's heating.
Well, both of these were in the tornado at the house. I'm going to fix them.
Yeah, well, like I said, all you need to do is just look them up. And I'd almost guarantee you could buy just about any vacuum tube you need.
Well, I got part of the vacuum tube.
And if you ever went up to like these guys can handle, we can design these things to handle millions of watts of power. So I guarantee if you went up to one of these television stations that still doing broadcast, their output starts vacuum.
You know what you need is like this. Somebody Jones picked off over the radio. You can pick up South America and places like that.
Well, you can do that with transistors. I mean, it's just that transistors are not. They're not as forgiving. They don't.
You go across that dial and you can pick 10 stations speaking Spanish.
But the way the vacuum tube would work is we would have a metal that would emit an electron cloud, and we'd come up here and we'd put a heater in it. And then when you heated that up, it would emit electrons. And then what we'd do on the other side, we'd put something they called a plate, and we'd put a big positive potential there. And what did that do to the electrons? So electrons are negative. You put a big positive potential that causes it to do what? Flow. And then what we would do is they'd come up here and they would put these things they call grids in here. And then the grids would be biased to a negative potential. So what you could do, depending on the negative potential, you could control the flow of the electrons between the cathode and the plate. And that's the way tube amplifiers go. And you put more and more grids in there to give you more and more control. But what they found out, guys, is that we could take silicone and we could put pressure on silicone, and silicone there's a lot of semiconductors that varies its resistance with what? Pressure. So we could take these, and they operate similar to strain gauges, but strain gauges have to be warped. And they're really precise. These guys, you can just take them and press them like this, and then they'll change their resistance. So you can take these guys and just change. So what they'll do is they'll have a basic diaphragm inside the pressure sensor, and they have the semiconductor sensors on each side, and then they come up and put pressure, and then they average all these together, and then you get an output. It's fairly important. Similar to the silicone changes its resistance in stretch or block. So these are your solid state. Of course, these are very, very, very popular because of their basically their size. So these guys can be a lot smaller. These are what we're going to run into a lot. And if you get into older stuff, you're going to run into Gordon tubes, you're going to run into bellows, you're going to run into diaphragms, right? You understand? So these are probably the most popular out there now. Now, how this operates, I don't know, but this is whether it's got a bellows in there or what, I don't know. But this is the pressure sensor that I got off of one of my compressors. And of course, when you look at it, it's got a span on it. It says 100 to 70 psi. So as long as you're between 100 and 70 psi, then this guy right here would be off, right? You understand? Right? When you get up to 100 psi, I'm sorry, anything that's between 70, let's rephrase it. When it drops below 70 psi, this contact would be made, and it would stay made until it got up to what? 100 psi. and then it would open, and then it would drop down the water, 70 psi. So one of y'all that's working on your level sensors, that would be a two level control, right? So this was the tube that ran down to the tank. So our most popular pressure sensors out now are probably going to be solid state. And they're use semiconductors. Oh, they could use strain gauges too, but most of them use semiconductors. Notice they're mounted different ways. And they average them to one. The problem with semiconductors is they're not perfectly linear. A Bardon tube would be really linear, right? Understand that. Your other sensors would be linear. Semiconductors have a tendency of using four like this and then averaging them together. So that's it on pressure sensors, guys. Y'all got any questions? You picked up a lot of terms. Of course, they should be in the glossary that I've got up there. I'm working on the glossary. I need to upload a new one. I don't think I've made any changes to yours or not. So any questions on this? Everybody okay? We're short some people today. This came off my compressor. Well, it was a compressor. Wasn't mine. It was, we had a compressor. Before we got on the shop air over in the robotics lab, we had each robot had its own compressor on it. And that was mass confusion because they'd all come on at different times. And the one that was on the Fanuc robot, no, I'm sorry, the one that was on the KUKA robot died. In fact, I've got the compressor here.
This range is fixed, so you can't vary it.
No, you can't vary that range. That's true on most home compressors. Most home compressors run between 100 and 170 psi. So just about all the tools that you have access to are rated at 60 psi. This is the actual compressor right here. And it's a reciprocating compressor, which is a pretty standard compressor. Where's my camera at? Did I close it down? Yeah. So they call it a reciprocating compressor. So it's got a universal motor, which is a series motor. A series motor has brushes in it, and this is what happened to this one. The brushes went bad and burned up the commutator. So if you look at the commutator on there, you see it's in very, very bad shape. And then it ran through a gearbox. You can see it uses a cam type situation that converts a rotary motion into a linear motion. So this is basically the way your car works. And then it's counter offset to compensate for the weight of the piston, right? So if you ever took the cam out of your car, it would look very, very similar to this. But this is this came off of that. This actually went to the tank, and then that was connected into the tank to measure the pressure in the tank to determine when the compressor run. So this is a pretty standard compressor. It's just little. So this was the compressor that ran the Fanuc robot over there. It's basically unrepairable because of it it tore the commutator up on the series motor. Series motors are sometimes referred to as universal motors because they'll run on AC or DC, which is pretty neat. You know that took motor controls. What's the advantage of a series motor? Nobody remembers. So a series motor has very poor speed regulation, but it has extremely high torque characteristics. So we have to start that thing under load. So as soon as you do it, there's already pressure, probably pressure in your tank, right? You understand? You got to put more pressure in there. So series motors have a really high starting torque. They have a real high run torque, but they have very poor speed regulation. Your hand drill probably uses a series motor. So, you know, you put it up in the air, it turns real fast. As soon as you put it into an object, what happens? Slows down, but then the torque goes what? Up, yeah. So you get into some of these hand drills, you got to be careful because they'll break your wrist. I mean, that's how much. So that's the advantage of series motors. So anything that has to create, anything where torque has to go up when load goes up, is going to use a series motor. So your starter on your car is a what? Series motor, right? So that's it, guys. Any questions? Okay, we got one more thing we're going to go through. We might touch on one, and we'll do that next class. So the next thing we're going to look at, and the PowerPoints are up there. So the next thing we're going to look at is flow sensors. And we might touch on vision sensors if you have time. Flow sensors. And that would be all the sensors that we're going to touch in this class. Does this mean that's all the sensors that's out there? And we have sensors that sense color. We have sensors that sense all different types of things. The viscosity, the thickness of something. We have the thickness of a liquid. And then we have sensors that sense thickness of metals. We had an X-ray machine out on the Galvin line at U.S. Steel. They used X-ray to measure the thickness of the coating that they did when they put the zinc coating on the metal strip. They could actually measure the thickness of the coating to make sure it was within the limits of the metal that they were running. So I got to play around with X-ray a little bit. So there's a lot of things that you just don't have time to get into. So when you get out there, guys, you might run into sensors that we don't talk about, but at least they all do the same thing. And what does the sensor do for us? What do sensors do?
Convert the physical when electrical.
Yeah, converts the physical into electrical. They're all going to do. They all do basically the same thing. It's how they do it, right? You understand that change. All right.